Hi everyone, in this video we will talk about error analysis. First, you can look at the confusion matrix. You need to make a prediction using the cross-validation prediction function, then call the confusion matrix function. y_train_prediction equal to cross-validation prediction SGD classifier x_train_scaled, y_train, CV equal to 3. Confusion matrix variable equal to confusion matrix open parenthesis y_train, y_train_prediction. The result equal to this. That's a lot of numbers. It's often more convenient to look at an image representation of the confusion matrix. Using matchShow function, plt.matchShow open parenthesis confusion matrix variable, cmap equal to plt.cm.gray close parenthesis. Save underscore figure open parenthesis confusion matrix plot, tight layout equal to false close parenthesis. plt.show. This confusion matrix looks fairly good since most images are on the main diagonal, which means that they were classified correctly. The 5s look slightly darker than the other digits, which could mean that there are fewer images of 5s in the data set, or that the classifier doesn't perform as well on 5s as on the other digits. Let's focus the plot on the errors. First, you need to divide each value in the confusion matrix by the number of images in the corresponding class. So, you can compare error rates instead of absolute number of errors. Row sums variable equal to confusion matrix variable dot sum open parenthesis access equal to 1, keep dimension equal to true close parenthesis, norm confusion matrix variable equal to confusion matrix variable divided by row sums variable. Now let's fill the diagonal with zeros to keep only the errors, and let's plot the results. np dot fill dimension open parenthesis norm confusion matrix variable, 0 close parenthesis. plt dot match open parenthesis norm confusion matrix, cmap equal to plt dot cm dot gray close parenthesis. Save figure open parenthesis confusion matrix scores or confusion matrix errors plot, tight layout equal to false close parenthesis, plt.show. Now you can clearly see the kinds of errors the classifier makes. Remember that rows represents actual classes while columns represents predicted classes. The columns for classes 8 and 9 are quite bright, which tells you that many images get misclassified as 8s or 9s. The rows for classes 8 and 9 are also quite bright, telling you that 8s and 9s are often confused with other digits. Conversely, some rows are pretty dark, such as a row 1. This means that most ones are classified correctly. A few are confused with 8s, but that's about it. Notice that the errors are not perfectly symmetrical. For example, there are more 5s misclassified as 8s than the reverse. Analyzing the confusion matrix can often give you insight on ways to improve your classifier. Looking at this plot, it seems that your efforts should be spent on improving classification of 8s and 9s, as well as fixing the specific 3 and 5 confusion. For example, you could try to gather more training data for these digits. Or you could engineer a new feature that would help the classifier. For example, writing an algorithm to count the number of a closed loop. 8 has 2, while 6 has 1, while 5 has none. Analyzing individual errors can also be a good way to gain insight on what your classifier is doing and why it is failing. But it is more difficult and time-consuming. For example, let's plot examples of 3s and 5s. Class A variable, comma, class B variable equal to 3, 5. X underscore AA equal to X underscore train, Y train, or Y underscore train equivalent to class A, and Y underscore train underscore prediction equivalent to class A variable. X underscore AB equal to X underscore train, Y underscore train equivalent to class A, and Y underscore train underscore prediction equivalent to class B. X underscore BA equal to X train, Y train equivalent to class B, and Y underscore train underscore prediction equivalent to class A. X underscore BB equal to X underscore train, Y underscore train equivalent to class B, and Y underscore train underscore prediction equal to class B. plt.figure size equal to 8, 8. plt.subplot 221 semicolon plot underscore digits open parenthesis X underscore AA first 25 image, comma, image pair row equal to 5. plt.subplot 222 semicolon plot underscore digits X underscore AB first 25 image, comma, image pair row equal to 5. plt.subplot 223 semicolon plot underscore digits X underscore BA first 25 image, comma, image pair row equal to 5. plt.subplot 224 semicolon plot digits X underscore BP first 25 image, comma, image pair row equal to 5. Save figure. plt.share. The two blocks on the left show digits classified as 3s, and the two blocks on the right show images classified as 5s. Some of the digits that classifiers gets wrong are so badly written that even a human would have trouble classifying them. However, most misclassified images seem like obvious errors to us, and it's hard to understand why the classifier made the mistake it did. The reason is that we used a simple SGD classifier, which is a linear model. All it does is assign a weight per class to each pixel, and when it sees a new image, it just sums up the weighted pixel intensity to get a score for each class. So, since 3s and 5s differ only by a few pixels, this model will easily confuse them. The main difference between 3s and 5s is the position of a small line that joins the top line to the bottom arc. If you draw 3 with the junction slightly shifted to the left, the classifier might classify it as a 5 and vice versa. In other words, this classifier is quite sensitive to image shifting and rotation. So, one way to reduce the 3 and 5 confusion would be to pre-process the image to ensure that they are well centered and are not too rotated. This will probably help reduce other errors as well. Thanks for watching.